In late 2017, an object from another star system tore through our solar neighborhood, moving faster than any known comet, then quietly breaking the rules of gravity as it left. This strange visitor was named Oumuamua, and its brief appearance still challenges astronomers years after it vanished into interstellar darkness. Astronomers quickly realized this was not a native comet or asteroid on an elongated loop, but the first confirmed interstellar visitor, officially labeled 1I 2017 U1, crossing our system on a one-way hyperbolic trajectory back into deep space. Nothing like it had been seen passing close to the Sun before. Our solar system is not isolated. It sails through the Milky Way, plowing through dust, dark matter, and stray comets. Every atom in your body once drifted through this same galaxy, shaped by the same gravity steering Oumuamua past our Sun. Before Oumuamua, theory predicted our skies should swarm with unseen visitors. Some estimates suggested up to 10,000 interstellar objects pass within Neptune's orbit every day, most tiny, dark, and undetectable, silently threading through the outer solar system without anyone ever noticing. To understand why so many wanderers exist, we start at our own frontiers. Beyond Neptune lies the Kuiper Belt. Then far beyond that, an enormous spherical reservoir called the Oort cloud, possibly holding trillions of icy bodies weakly bound to the Sun. Passing stars tug on this distant cloud. Even a flyby a couple of light years away can slightly reshape orbits, sending some comets inward on million-year journeys, while flinging others completely free, creating unbound interstellar objects that drift between stars forever. Because nearly every star likely has its own Oort cloud, the galaxy continuously trades comets. Our solar system plows toward the constellation Lyra. So many interstellar interlopers approach from that direction, briefly feeling the Sun's gravity before continuing on their ancient paths. Oumuamua was almost certainly one of these long-lost fragments. Tracing its incoming path suggests it came from near the bright star Vega in Lyra, entering the solar system from above the ecliptic, before swooping inside Mercury's orbit and rushing back outward. Humans only noticed after it was already leaving. On 19 October 2017, the Pan-STARRS telescope at Haleakalā Observatory in Hawaii detected a faint, fast-moving point of light, initially catalogued as a comet, then reclassified as an asteroid when no surrounding coma appeared. When its orbit was computed, astronomers saw it was unbound from the Sun, following a hyperbolic curve that would never return. The International Astronomical Union created a new category, I for interstellar, and this strange visitor received the Hawaiian name Oumuamua, meaning distant scout. Measurements suggested Oumuamua was remarkably small by astronomical standards, perhaps between 100 and 400 meters long. Its brightness rose and fell every 7 hours, varying by a factor of about 10, implying an extremely elongated or flattened body tumbling end over end as it rotated. Unlike most asteroids, Oumuamua did not spin neatly around one stable axis. Analyses show it was in a complex tumble called non-principal axis rotation, as if some past event had jostled it, leaving it wobbling chaotically through space while sunlight flashed rhythmically from its surfaces. If Oumuamua behaved like an asteroid, it should have formed in the rocky inner regions of some distant planetary system. Somehow it had to be ejected by colossal gravitational interactions or collisions, survive eons in interstellar space, then randomly intersect our small patch of the galaxy. Yet composition and shape were not the real shock. As Oumuamua swung past the Sun on 9 September 2017, racing at about 87 kilometers per second, astronomers noticed it was not slowing as expected. Instead, its trajectory showed a tiny but persistent extra acceleration outward. In physics, motion only changes when forces act. For ordinary asteroids, gravity alone curves their paths. Here, calculations showed gravity, and normal solar radiation pressure could not fully explain Oumuamua's deviation, even though the added speed near perihelion was only about 17 meters per second. Scientists turned to comets for comparison. When sunlight warms their ices, gas jets vent into space, creating comas and tails that act like tiny thrusters. But telescopes saw no visible coma around Oumuamua, and the Spitzer Infrared Observatory detected no dust or warm gas whatsoever. Spitzer's non-detection also limited Oumuamua's size and suggested it reflected sunlight unusually well, perhaps 10 times better than a typical comet nucleus. That shiny, compact, comet-like yet cometless nature deepened the mystery, opening space for explanations ranging from exotic ices to deliberately engineered alien technology. One of the boldest ideas came from Harvard astrophysicist Avi Loeb, who proposed that Oumuamua might be a light sail, a very thin sheet pushed by starlight. If only a few tenths of a millimeter thick, sunlight pressure alone could produce the observed acceleration without any gas jets. The same photons warming your skin also push on spacecraft hardware. Solar sail experiments in Earth orbit already harness this faint pressure for propulsion. If nature or technology sculpted Oumuamua into a thin sheet, it would ride that same gentle force across interstellar space. Other researchers preferred a natural explanation. Daryl Seligman suggested Oumuamua might be made largely of frozen hydrogen. As it approached the sun, invisible hydrogen gas would sublimate away, providing thrust like a rocket while remaining undetectable in our telescopes, since cold hydrogen emits little infrared radiation. Loeb and collaborators pushed back. They calculated that even the weak starlight between systems would gradually warm any pure hydrogen iceberg, causing it to evaporate long before reaching us. That made such blocks extremely difficult to form and preserve over interstellar distances in realistic molecular clouds. The hydrogen idea evolved again when Jennifer Bergner pointed to experiments with irradiated water ice. Under cosmic ray bombardment, hydrogen can become trapped in microscopic pockets inside ice, then slowly leak out when warmed. Oumuamua might therefore be mostly water ice, releasing hidden hydrogen rather than being pure hydrogen itself. Seligman and Bergner argued that Oumuamua fits a new class they called dark comets. These are icy bodies whose gas escapes invisibly, without bright dust tails, because trapped hydrogen seeps through the structure itself instead of erupting in visible jets, still imparting a measurable non-gravitational push. The debate between light sail advocates and dark comet supporters remains unresolved because Oumuamua faded beyond detection within weeks. Without new observations, the object became a kind of Rorschach test for planetary science, highlighting how little we truly know about the diversity of small bodies between stars. To move beyond speculation, Seligman, Bergner, and others scoured data on known near-Earth asteroids, searching for subtle non-gravitational accelerations. They identified 6 small objects that appear asteroid-like yet drift slightly from predicted orbits, without visible comas, making them prime dark comet candidates much closer to home. One of these, 1998 KY-26, is already scheduled for a close visit by Japan's Hayabusa 2 spacecraft extension. Only about 30 meters across and spinning once every 10 minutes, it may reveal whether invisible outgassing truly nudges some apparently inert near-Earth asteroids. The same gravity keeping your feet on Earth also sculpts these tiny worlds. Understanding how sunlight, rotation, and subtle gas leaks move small asteroids improves our models of potential impactors, future mining targets, and even the long-term stability of satellites and space debris around our planet. While theory swirls around Oumuamua, our second confirmed interstellar object, 2I Borisov, looks much more familiar. It displayed a classic comet coma and tail almost 14 Earth diameters across, shed material near perihelion, and followed a path largely explained by gravity alone, behaving like an ordinary long-period comet. Interstellar visitors are not always born that way. The comet C1980 E1 once orbited the Sun on a 7 million-year ellipse, reaching more than 1 light-year out, until a close encounter with Jupiter in 1980 flung it onto a hyperbolic course that will eventually escape forever. The reverse can also happen. Some comets, such as Mach-Holtz 1 and Haleakalā C1996 B2, have highly unusual chemical compositions and elongated orbits, hinting they may have originated around other stars before Jupiter's gravity slowed and captured them into permanent membership within our solar system. One particularly strange case is the asteroid 514017 Haleakalā, which shares Jupiter's orbital period yet travels in the opposite direction, on a retrograde path. Its unusual orbit and likely depleted volatiles suggest it could be an ancient captured interstellar object that long ago lost its cometary activity. For Oumuamua itself, astronomers rewound its trajectory through computer simulations, tracing its motion backward across millions of years. It seems to have passed through the general region of Vega and several other nearby stars, but uncertainties in stellar motions mean no single birthplace can yet be identified. Today, Oumuamua is more than 6 billion kilometers away, heading toward the constellation Pegasus at roughly 26 kilometers per second, at a distance similar to Voyager 1 when it captured the famous pale blue dot image of Earth suspended in a shaft of sunlight. Catching such a small, dim object is extraordinarily difficult. Oumuamua was only discovered 40 days after perihelion and already 33 million kilometers from Earth. Within 2 months it dimmed beyond the reach of large telescopes, leaving any future mission to home in on an essentially invisible target. Project Lyra, a study from the Initiative for Interstellar Studies, explored how an ambitious probe might still catch up. One option uses a gravity assist at Jupiter, then a dive close to the Sun where engines fire at maximum speed, a maneuver called a solar Oberth burn. By burning fuel where the probe is already moving fastest, this trajectory could exit the solar system at over 70 kilometers per second. However, skimming so near the Sun demands a massive heat shield, reduces payload, lengthens the route, and relies on complex maneuvers never yet demonstrated in flight. A second proposed path avoids that extreme dive. The spacecraft would launch from Earth, swing by Venus, then Earth twice, finally using a powerful gravity assist at Jupiter to slingshot outward toward Oumuamua's trail, reaching high speed without requiring a heavy heat shield or untested close solar operations. Even if this particular rock is never chased, new surveys will reveal many more. The Vera C. Rubin Observatory will repeatedly image the southern sky, building the legacy survey of space and time, and potentially discovering dozens of Oumuamua-sized interstellar visitors each year. ESA's Comet Interceptor mission will take a complementary approach. It will launch to a gravitational parking point, wait quietly for several years, then sprint toward a newly discovered comet or interstellar object, performing a rapid flyby to map its surface and surrounding gas in unprecedented three-dimensional detail. In the decades ahead, the universe and beyond will have many more interstellar visitors to explore. Whether Oumuamua was a dark comet, a fragment of alien engineering, or something stranger, it reminds us that every small rock crossing our sky can rewrite how we understand the wider cosmos.